Welcome back to another explainer. Today, we're taking on a really fascinating challenge straight out of Chapter 2, demystifying inverse trigonometric functions. I mean, if you've ever stared at a repeating sine wave and thought, how on earth am I supposed to put that infinite rolling thing into reverse, you are exactly in the right place. We're going to break down this whole concept visually, logically, and completely.
Here is our roadmap for today. First, we'll tackle the reversibility problem. Then, we'll work on taming sine and cosine, followed by cosecant and secant, and tangent and cotangent. And finally, we'll wrap up by actually finding principal values.
Section 1. The reversibility problem. Reversing repeating waves.
So there's this massive clash between what an inverse mathematical operation requires and what trigonometry actually does. How exactly do you reverse a repeating wave? This one simple question really sets up the central mystery of the entire chapter. Think about a standard sine or cosine wave. It just goes up and down over and over again, from negative infinity to positive infinity. But to go backwards, to mathematically reverse a function, you need a clear, single path back to the origin. Trying to reverse a function that literally never ends, that is a massive mathematical roadblock.
To really understand why this is such a roadblock, we got to look at the basic rules of the road. Remember back in Chapter 1? We learned that for an inverse to even exist, the function absolutely must be a bijection. That means it's 1-1, where each output comes from exactly one unique input, and it's onto, meaning every possible output is covered. If a function fails those conditions, its inverse simply cannot exist. Period.
And here's the kicker. Standard trigonometric functions fail this requirement completely. Because they are endless repeating waves across their natural domains, they spit out the exact same output value infinitely many times. Imagine drawing a horizontal line straight through a sine wave. It crosses that curve again and again. An output of 0 comes from an input of 0, pi, 2 pi, and so on. It is incredibly far from being 1-1.
Section 2. Taming sine and cosine. Restricting the domains.
But of course, mathematicians don't just give up. The basic rule for an inverse function is that it's just a mirror image reflected perfectly across the diagonal line y equals x. Notice what happens when you take that original horizontal sine wave and literally flip the x and y axes. You get this really cool vertical snake-like curve. But there's a huge catch here. A vertical repeating wave isn't a valid mathematical function because a single input on the x-axis suddenly gives you multiple outputs on the y-axis. We've got to fix that.
So, to make this inverse a true function, we have to quite literally fence it in. We take the standard domain of the sine function, which normally spans all real numbers, and we severely restrict it. We basically chop off the rest of the endless wave and only isolate the specific section from negative pi over 2 to pi over 2. We call this our restricted principal value branch. Inside this tight little box, the function hits every value from negative 1 to 1 exactly once. Bam! Now it is 1-1 and onto. Now it has a valid inverse.
Now, what's really fascinating here is how cosine requires a totally different fence than sine. Standard cosine also fails that horizontal line test, but we can't just restrict it to that same negative pi over 2 to pi over 2 interval. Why? Because cosine is actually positive on both sides of 0. It goes up to 1 and right back down. That is absolutely not one-on-one. Instead, we restrict cosine's domain from 0 to pi. This creates a perfect, non-repeating curve that drops from 1 smoothly down to negative 1. Because of that, the inverse cosine domain becomes negative 1 to 1 with an output range strictly locked between 0 and pi.
Section 3. Cosecant and secant. Managing the asymptotes.
Because the original secant and cosecant functions involve dividing by sine and cosine, their graphs don't just wave smoothly, they shoot off into infinity the second that denominator hits 0. That creates these massive vertical asymptotes. As a result, the inverse graphs end up fractured. They're split into pieces with distinct gaps that we really have to navigate carefully when defining their boundaries. To keep our perfect 1-1 mapping intact without breaking the laws of math, we use the exact same primary branches as sine and cosine, but we perform a bit of surgical extraction. Cosecant is 1 over sine, right? So it's undefined wherever sine is 0. Therefore, its restricted domain is negative pi over 2 to pi over 2 minus the exact point 0. Secant is 1 over cosine, so we use the interval 0 to pi, but we strictly subtract pi over 2. We essentially take our fenced-in domain and just pluck out the exact points that would cause an error.
Section 4. Tangent and cotangent, constrained curves.
The inverse tangent function forms this incredibly smooth, constrained curve, while the original tangent function features all these repeating vertical curves squeezed between asymptotes. Reflecting that across the line y equals x causes the inverse tangent function to elegantly flatten out, trapped perfectly between horizontal boundaries. It stretches on forever from negative infinity to positive infinity along the x-axis, but it never escapes its vertical limits on the y-axis.
Speaking of limits, there is a super vital distinction to make here. Compare sine's closed interval, which uses solid brackets, with tangent's open interval, which uses parentheses. Because the original tangent function involves dividing by cosine, it literally explodes to infinity right at negative pi over 2 and positive pi over 2. It simply does not exist at those exact spots. That is why we use open parentheses to define its principal value branch. The curve gets infinitely close to those bounds, but it is absolutely never allowed to touch them.
Section 5. Finding principal values. Solving inverse trig.
All right, it's time to bring all this fascinating theory together into a practical tool. This table right here, this is your master cheat sheet. It synthesizes exactly how every single function gets restricted to become invertible. We've got the inverse sine safely bounded between negative pi over 2 and pi over 2. Inverse cosine neatly slotted between 0 and pi. You can see the precise points carved out of cosecant and secant and those open boundaries of tangent and cotangent. Every single time you solve an inverse trig problem, your final answer absolutely must live securely inside the range given in that rightmost column.
Let's walk through a quick example from the text to see just how satisfyingly simple this is in practice. Step 1, we want to find the principal value of the inverse sine of 1/2. We start by setting that expression equal to a variable, let's say y. This lets us flip it back into a standard trig equation. Sine of y equals 1/2. Step 2, check the cheat sheet. We recall the principal value branch for sine is fenced securely between negative pi over 2 and pi over 2. Step 3, use your standard trig knowledge to find the specific angle within that fence where sine equals 1/2. That angle is pi over 6. Step 4, conclude your answer. The principal value is pi over 6. You just flip it, find the angle, and ensure it's inside the fence. It's really that simple.
So, you've completely demystified the mathematical challenge of Chapter 2. But I want to leave you with this thought. Now that you know how to mathematically reverse the fundamental ways of nature, what are you going to build with it? Remember, these inverse functions aren't just abstract rules trapped on a chalkboard. They are the essential keys to unlocking incredibly complex calculus integrals that engineers and scientists use every single day to map out everything from fluid dynamics to the structural integrity of bridges. The power to reverse the wave is basically the power to engineer reality. Thanks for joining me on this explainer, and keep focused out there.